Okay, hello everybody. Before we get into section 7.4, something called partial fraction decomposition, I want to remind you that suppose I give you a quadratic in the general form. Now you'll remember from algebra you could take these two guys, put them together, factor out, and then do the difference of two perfect squares. Oops, I forgot the parentheses there. And so you could write the standard form or the general form, or in this particular form, or even possibly in this particular form. And why would you want to be able to write the same quadratic in three different ways? Actually, there are more ways, but I don't want to get into discussion of that. Well, this way is very easy to differentiate. This way is very nice because your h comma k is the coordinates of your vertex. And if I write it in this form, I'm able to pick up where my intercepts are at. Okay, so I have it in factored form. So depending upon the question that you're going to be asking, this might be more preferable over this one, or this one might be more preferable over this one. And in fact, those of you that are going to go on to graduate school, and if you take something called numerical analysis, you'll find out that when you go to actually evaluate, like a quadratic, cubic, etc., the way in which you evaluate that polynomial actually can change the accuracy of your result. And so the point of that little diversion is the following. So this is section 7.4 on partial fraction decomposition. And so the question comes up is, how in the world am I going to differentiate that? Now you could try to put in trig identities here, because I see an x squared minus a 1 squared. That's one possibility. And then so you make your substitution, and then you substitute in here, then you have to substitute here, and you're in the realm of trigonometric problems. But the idea here in this section is that I could actually write my bring the microphone a little closer. So I notice that the denominator is really the difference of two perfect squares. And so a question comes up is it possible to take this and break it up into two pieces? And the reason for that, so the question comes up is, can I actually take this and break it up into two pieces where a and b are some as of yet undetermined constants? And the reason for that is because then this would become an ln problem. Your u would be x minus 1. Here your u would be x plus 1. So in other words, we could take a product and decompose it into two partial fractions. And so the question is, can we do that? And how do we do that? And it's going to turn out that the answer to that depends on whether or not this guy has factors. Okay, so here's what we do. We go ahead and say, okay, I'm going to decompose this rational expression into two fractions. And I want to find out what my a and my b is. Now, because I don't like to work with fractions, I'm going to multiply both sides by x minus 1 times quantity x minus 1 times quantity x plus 1. And what that's going to do is that's going to get rid, so I'm going to multiply it by this on this side and this side, and that's going to get rid of the fractions. So if I multiply both sides by x minus 1 times x plus 1, we get cancellations, and we get one cancellation here and one cancellation here. So this now just becomes 1 times 5x minus 1. And then we have this. So what we've done is we've just multiplied by the least common multiple, really. And so now we have no more fractions. And so what I want to do is I want to see if I can figure out what my A is and my B. I want to pin those down. Now, when I look at this problem right here, if I choose x to be a -1, then I could put it in here, but then what would happen here? The A part would disappear, and a -1 minus a 1 is a -2, so I could figure out what the B is. Or if I chose x to be 1, then this would be gone, and this would become a 2, and then we could put 5 minus 1, so you'd have 4. So we see the simplest values for this particular example are plus and minus 1. Okay, so if I take x equals 1, and I substitute it in here, here, and here, notice that the B part is gone. So I have a 1 plus a 1, which is going to be a 2, and I put a 1 in here. And so I can isolate my A. So that means I have 2A equals 4, so A has got to be 2. So I now know what this guy is. Okay. So if I put the 2 in there now, I now have some more information. So I now know what my A is. So I've used up the, excuse me, I've used up the 1, so now we're going to use the -1. And notice what happens is this guy is gone. And we have a -1 minus, which is a -2. I put the -1 in here, so I'm going to get -5 minus 1, which is a -6. So we now have -6 equals -2b, so b has to be what? 3. So I now know how to break up this single expression into two partial fractions. And so instead of integrating this, I'm going to integrate this one and this one. And you could actually check. So you could find the what? Least common denominator is going to be x minus 1 times x plus 1. So you're going to multiply this by x plus 1 over x plus 1. And you're going to take the second one. You've got the x plus 1. You're missing the x minus 1. So you're going to multiply by 1. This guy says that. And then you just do the algebra. So you've got 2 times x plus 1 plus 3 times x minus 1. Expand everything out. Now you can put them both under the same common denominator. And if you put that together, so you've got 2x plus 3x, which is your 5x. And 2 minus 3, which is a -1. And so you have done this correctly. So the point of that is, we now have, instead of doing this integral, we're going to do two integrals. So each one of these looks like an ln. It looks like a 1 over u du. So what I'm going to do is, let's break this up into pieces. So I'm going to take the 2 outside, and I'm left with x minus 1 downstairs. And so this is going to be my u, and this is going to be my du. I don't have to put a constant in and take one out. So this is going to be a 1 over u du problem, which is an ln. And we have to put absolute values because we don't want to be in the complex plane at this point. So we're going to get 2 ln. You're going to get a constant of integration here from this one. You're going to get a constant of integration here. We're going to put those two together. We'll just call it a constant of integration. And if I look at the other integral, so we know constants come out in front. This is going to be a 1 over u problem du. So this becomes 3 ln of x, absolute value of x plus 1, plus a constant. And so now what we do is we just put the result of this one together and this one, and then we put the two constants of integration together, and we get this guy. Okay, now the book is going to take this further. So as far as I'm concerned, this is completely acceptable. The book, however, is going to take this and bring it in as an exponent, and same thing here. And addition with logarithms just means you're multiplying, right? So they're going to put the 2 as the exponent, and the 3 as the exponent, and then addition becomes multiplication. So the book is going to come up with this. They're going to put this one together times this, and you get this. As far as I'm concerned, this is completely acceptable. Your book, however, is going to possibly take it farther. Okay, so now let's take a look at number 12. So I would like to know, so the difference between this problem and the previous problem is now I have to find the factorization of this. Now, you could just look at this and say, okay, a positive 6 and a negative 5, that means this is both going to have to be negative, and we know the factors of 6 are 1 and 6, 2 and 3. The 2 and the 3 is going to give us the 5. But let's pretend we don't know that. So what I do is I take my x squared minus 5x plus 6, and I want to remind you about long division. So if I take, so I'm going to pull out of thin air the number 1, okay? There is no rhyme or reason. I'm just picking a number out of thin air. And I'm going to evaluate this polynomial at 1. So I take 1 squared minus 5 times 1 plus 6. And so if you do the arithmetic, you get 2. So you're going to get 1 minus 5 plus 6. So this is, 6 plus 1 is 7 minus 5 is 2. Okay. Again, where did I get the 1? I just pulled it out of thin air. All right? But I'm trying to remind you about long division. What I'm going to do now is I'm going to take x minus this number, and I'm going to I'm going to divide it into this. Now, if I pick correctly, if x minus 1 is really a factor of this, we will get a remainder of 0. Let's see what happens. So, I'm trying, again, where did the 1 come from? Just out of, where did the 1 come from? Out of thin air. I'm just making up the number. And there's a fundamental theorem of algebra that says if I pick a number and I go x minus that number and I divide into this polynomial, I'm going to end up with a remainder. And I want to show you that that remainder is in fact 2. Okay, so you remember from long division the following. So I'm asking myself the question, what do I have to multiply x by to get an x squared? Well, that'd be an x. Put it in the x column. X times x is x squared. X times negative 1 is a negative x. Now students find, so you're going to do a subtraction, and I think students find, I put a little circle on what the sign when you subtract. So this was positive, becomes negative. This was negative, it becomes positive. And when I add these two guys up, the x squared should, what? Disappear. And now I have x minus 5x, which is a negative 4x. Now we have a problem. We have a single digit object and a 2-digit. We bring down the 6. And now I ask the question, what do I have to multiply x by to get me a negative 4x? Well, a negative 4. So now we take this times this, negative 4 times that, and we get that. So we subtract, so what was, what was negative now becomes positive. What was positive now becomes negative. And so if I've done this correctly, yeah, the x's cancel, and I've got, 6 minus 4, which is 2. And I want you to notice that that is, the remainder is what we get when we evaluate the polynomial at a number. So the point of this is if I can find somehow a number that makes the p of that number disappear or become 0, I found a factor. So a fundamental theorem of algebra says if p is just an arbitrary polynomial, real value polynomial, let's start with that, then evaluating p at some constant is the remainder of the long division. In other words, if I take x minus that number and I divide it into this, the remainder is the P of C. So let's go back to our problem where we had the x squared minus the 5x plus 3. And I'm going to pick out a 2. Okay, and the reason I know that is because the 6 is 1 and 6, or 2 and 3, and the 2 and 3 is going to give us the 5 there. So if I put in a 2 here, so 2 squared minus 5 times 2 plus 6, which is 4 minus 10 plus 6, and that is 0. That means the remainder of the division of x minus 2 into this guy has a remainder of 0, which means x minus 2 is a factor of that. So let's verify that. Let me take x minus 2 and divide it into this. So I ask myself the question, what do I have to do to x to get an x squared? Well, we're going to multiply it by x, put it in the x column. So x times x gives me x squared, and then x times minus 2 is a minus 2x. Now negate. What was positive now becomes negative. What was negative becomes positive. The x squareds have canceled. And I'm left with minus 5 plus 2, which is a negative 3x. So now I have a, quote, 1-digit number, but I have a 2-digit object. So I bring down the 6, and I ask, what do I have to multiply x by to get me a negative 3x? I put a negative 3, and I multiply everybody. So if I do that, I get a negative 3x and a positive 6, and notice the remainder is what? Indeed 0. So I know how now to factor. This guy is this times this with a remainder of 0. We factored. So what this is saying is I can rewrite the denominator as this. So now we're going to do a partial fraction decomposition. I'm going to ask, can I write this thing as something, a number over this one plus a number over this guy? So we bring it down and we ask, can we find numbers a and b so that this side, the left side, equals the right side? Well, we're going to play the same trick. I do not want to work with fractions, so I'm going to multiply by the least common multiple, which is x minus 2 and x minus 3. So if I multiply both sides, the x minus 2's and x minus 3's cancel, and we're left with, so the x minus 2's here are going to cancel, I'm left with x minus 3. The x minus 3's are going to cancel, and I'm left with an x minus a 2. And so now, I'm not working with fractions, and I'm asking now, can I pin down what the a's and the b's are? So if I put in the simplest value, one of the simple values for x is a 3, and that wipes out this guy. And I put in an x here, and I put in a, excuse me, I put a 3 here and a 3 here. So we get 3 minus 4 is a negative 1, and 3 minus 2 is 1. So we now know that b is equal to a negative 1. So that gets us to negative 1. So now we do the same thing. We multiply both sides again. So we're back over here. So if now I choose to wipe out the b term, which we know is a negative 1. So now I use the x equals 2, and I put it in here, and this guy is wiped out. So then we get 2 minus 4, which is a negative 2. 2 minus 3, which is a negative a. So a has to be 2. So what I've done is, instead of looking at this thing, I'm going to break it up into two fractions. So in other words, in order to integrate this, I'm going to integrate each of these individually. Okay, so let's take this separately. So if I take the 2 times the x minus 1 over x minus 2. I just took the 2 out. And then here we didn't have to take out anything. So this is going to be the logarithm of absolute value of x minus 2. This is going to be the logarithm of x minus 3. And then we have a constant of integration. As far as I'm concerned, this is perfectly acceptable. Okay. However, the book is going to take it further. What are they going to do? The 2, oops, sorry about that. The 2 is going to come up as an exponent. So there's where the exponent comes from. And then subtraction, you'll remember, becomes what? Division. So you're going to have the absolute value quantity upstairs, x minus 2 squared, divided by the x minus 3, and then plus a constant. So we have solved our problem. Okay, so let's continue on. Let's take a look at number 16. And I want you to notice something here, that the degree of the polynomial on the top is an x cubed and an x cubed on the bottom. So the first thing I'm going to do is the following. I'm going to divide this into this. Explain why here in a minute. So we're going to do long division. So in other words, I'm not trying to factor anything yet. I'm just trying to get this down into a number plus some other things that are a little bit less complicated. So I take x cubed plus x squared divided into this. So I ask the question, what do I have to do to x cubed to get me an x cubed? Well, I multiply it by 1. So I take x cubed plus x squared. I subtract. That gets rid of the x cubed. And I have 4x squared plus x squared, which is what? 3 of them. And then I bring down the x and bring down the 1. Now, we can't do this into this, otherwise we'd start introducing 1 over x's. So the point of this is that this divided into this is this plus a remainder. So in other words, when we do this division, it means this divided into this is this plus this over this, which is my remainder. Oh, excuse me, down here. And notice that the degree now is higher in the denominator than it is in the numerator. That's going to be important. Okay, so if we take this further now, if I think of the, so I'm just going to work with this. I'm going to forget about the 1. Okay, so if I think of the denominator as x, so there's a common factor of x squared. If I pull that out, I get an x plus 1 times the x squared, and then try to do this. Now remember, ddt subscript 1 means don't do this. I'll show you that this is not going to work. And the reason it's not going to work is we're going to have a problem because we only have 2 constants that we're trying to determine. So don't do it this way. I'll explain how to fix it up. But first I want to show you what not to do. So if we do what we think we should be doing, that is writing this as it's a number over x squared plus a number over the x plus 1, then we go through the same process. We multiply both sides by this so that I don't have to work with fractions. When I multiply this side, the x squareds are going to cancel. I'm left with an x plus 1. And when I multiply here, the x plus 1s are going to cancel, and I'm left with an x squared. And notice no more constants. So if I choose x to be 0, this is gone, we're left with a negative 1. This is gone, and this is just 0 plus 1, which is a. So then supposedly my a should be a negative 1. And then in order to turn off this term, I'm going to choose x to be a negative 1. So we're going to put a negative 1 in here, negative 1 in here, and we get negative 1. So, and I put a negative 1 here, squared is 1. So b then equals, excuse me, a negative 1. So then supposedly, this can be written as the sum. Now we have to check this to make sure that this is actually correct. And what we're going to find out is we don't have the correct decomposition. So if I take a minus 1 over x squared minus 1 over x plus 1, so just pull out the negative and put these guys together. So then my common denominator is x squared and times x plus 1. So I'm missing the x plus 1 here, and I'm missing the x squared here. So then upstairs we're going to get x plus 1 plus x squared over my common denominator. And if I put these together, I'm going to get x squared plus x plus 1 over this guy. But this is what we started out with. This is not correct. And the reason it's not correct is because the assumption that we made previously was incorrect. And here's the problem. When I look at the 3x squared plus the x minus a 1, I have three constants. A 3, a 1, and a negative 1. And here, we only have 2 unknowns. So we really need 3 unknown constants. Or 3, yeah, because I have 3 coefficients of the of this guy. I'm really going to need 3 unknown parameters. So here's what we do to fix this. So what we do is we go back, and we had just said we're going to decompose this into this part and this part. The problem is that only gave us 2 unknown coefficients, because the left side, the polynomial here, if you think about it, we're going to be multiplying both sides by the x squared. So we're going to have a constant, and a constant. So we need 3 unknown coefficients. So what we do is the x squared, we have to add on another term, an x. So if this were x cubed, we'd have an x cubed, an x squared, and an x term. That's very important. So the problem is if you multiply both sides by the denominator, we only have the numerator, which has 3 constants, 3, 1, and negative 1. If you didn't do this, you'd only have 2. That's why we throw in another one. Okay, so we're now on familiar territory. So I multiply both sides by the x squared times quantity x plus 1. We get rid of the denominator, and we're left with this. So now we could turn off 3 things. We could choose x to be 0, a negative 1 right here, and then we're going to see that we run out of stuff, so we'll have to choose another number. So if I put in a 0, this is gone, this is gone, this is gone, this is gone, and I'm just left with this. So we're going to have a 1, a negative 1, and I put in a 0 here. So b times 1 is b, so b is equal to a negative 1. I now know what my b is. So let's turn off these terms right here. So if I choose x to be a negative 1, I put in a negative 1 here, which is 3. I get a negative 1, a negative 1, and a negative 1 wipes out this term and this term, so I've got c times negative 1 squared, which is a c. So 3 minus 2 is 1, so my c is equal to 1. So I'm now down to, let me fix this up a little bit. I'm now down to this guy right here. And we've already chosen 0 and a negative 1, so I have to choose something else. I've already used up. So in other words, we're not going to be able to turn off all these terms. So I've used up a 0 and I've used up a negative 1, so I'm going to choose a different number, which just adds a slightly bit more of some algebra. So if I choose x to be 1, I just substitute it into everything. And I get 3 on this side, and 1 minus 2 is negative 1. Add 2, so that add up this, so we get 2a equals 4, so a equals 2. So now I have partial fraction decomposition. And I'll let you go through the checking to make sure that it's correct. So what you're going to do is you're going to have to multiply this by x over x times x plus 1 over x times x plus 1. This is going to have to be, excuse me, x plus 1 over x plus 1. And this is going to have to be x squared over x squared. And if you go through the arithmetic, you can you'll find out that it does work. So I'll let you go through that. But the key step here was that you had to write so the first step, the difference here was because this is the same as this, and we're going to talk about what you do if you have when the degrees are even higher. So the first thing we did was a division, long division of this into this. We came up with 1 and then our remainder. Now we took our partial fraction decomposition and we broke that up into pieces. So this is going to give us an integral of dx, which is just going to be at x. Then we have our fraction, which we did a partial fraction decomposition, which is this guy right here. So then I could break this up. Remember that integration and differentiation, you could do them individually if you have sums or differences. So I'm just going to take this guy down, and this one down. And now we could do our integration. So this is going to be an ln. This is going to be the power rule, right? We're going to bring the x squared upstairs to make an x to minus 2. And this is a 1 over u du problem. So this is also going to be an ln problem. So if I do that, we end up with this guy right here. So I had a 1 over an x, I had a 1 over quantity x plus 1. Now we bring the x squared upstairs. So this is a, the power rule, right? So we're going to add a 1 and divide. And so I get this guy right here. So we take the add on a 1 and then divide by. And so this just becomes plus. And as far as I'm concerned, this is perfectly acceptable, okay? The book, however, is going to take it a little bit further. So the book is going to do the following. They're going to combine this guy, and they're going to put this one with this one. So you're going to put this one with this, and your expression. So we're going to take the ln terms and put them together. Now this is a multiplication, so this becomes a what? An exponent. And then we have to find the common denominator for these guys. Excuse me. So we put these two guys together. So the first thing is put that 2 in there. That's where this comes from. And addition, you'll remember, is multiplication. So I multiply the x squared times the x plus 1. Isn't that interesting? That shows up again as a logarithm. And then if we find the common denominator for these guys, it is going to be x. So this is going to be an x squared plus a 1 over an x. And this is my final answer. Again, if you get to this point for your quiz or your test, this is perfectly acceptable. You get 5 points. But just to remind you that if you get this answer, and the book gives you this answer, you know you have to do some additional algebra. I'm picking up this from example 7 because I was looking at this and I said, yeah, you bet this is kind of an important example. Downstairs, you have the denominator is factored or has been factored for you. Okay. Now, you'll notice that if you expanded all this stuff out, oh my gosh, you'd get a, what is this, a 6th degree, 8th degree, 9th, 10th degree polynomial. That's going to be a real mess. So they are being very nice to you and telling you what the factors are. So let's ask a question. What's the most number of times a single x shows up? Just once. If this was an x squared, you'd have to go a over x plus b over x squared. X minus 1 only shows up once. There it is. X squared plus 1 to the power of 3. And this is what is called like a prime polynomial. You cannot factor that over the real numbers. So you're gonna have to trust me on this. This is not factorable, and for the following reason: if you look at all the terms could be positive here, right? Now, actually, if you just graph this, you'll see that there's something very interesting coming about. So what we have to do is we've got to have something for this one. That's the A. We have to have something for this one. That's the B. Now, the problem is that for the x squared plus 1 cubed, we're going to have 1. And notice, because of the power of 2 here, I have to have an x and a constant. So notice that if the highest degree term in the denominator is 2, you're going to have an x to the first and a constant. And down here, you're going to have, again, it'll turn out the x plus the h, and this guy times this guy. And if we take a look, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 unknowns. Again, folks, the reason we have to do this is take a look at this term right here. When I cube a square, I get 6. So we can get 6 coefficients. 8, 9, and 10. So when you expand this out, you're going to get a polynomial degree that has many coefficients. You have to have as many unknown coefficients. So we're obviously not going to do that. Okay, let's take a look at number 42. And we have 1 over quantity 1 plus the cube root of x dx. And the question comes up is, what does this have to do with partial fractions? And so it looks like there's no relationship. And that is not quite correct. So you can see here in Calc 2, this is going to be a bunch of, oh yeah, let's try this, let's try this, let's try this. So I'm going to try something. I am going to, excuse me, I'm going to let u be the cube root of x for a moment. Okay, so what I'm saying is, this to me right here looks like a troublemaker. So this is not a square root. So we're probably not going to use trig substitution. So what I'm going to do is I'm going to call this troublemaker a u. And then so that we don't have to work with cube roots, I'm going to cube both sides. So that just means x can be written as u cubed. And so this means when I take the derivative, excuse me, I get a 3u squared. So I'm taking the derivative of this with respect to u, and then I just multiply. So I get dx is 3u squared du. Okay, so if I put all this stuff in, I get the following. So I made a substitution. I said let u be this, and then to undo the cube roots, I cube both sides. So I'm going to have to change, so I've changed from my x's to u's, but I also have to figure out what my dx is. So I differentiate this with respect to u, we get 3u and then u squared, and then just multiply by du. So I now know my dx, and I know what my u is. So when I do this, this becomes a 1 over 1 plus a u, and then the du, the dx I should say, excuse me, becomes 3u squared du. And then you can pull the 3 out, that's okay. And we're left with that. Notice the numerator has a higher degree than the denominator, so we're going to have to do long division. Now, instead of writing it as 1 plus u, we usually write in descending powers. So I'm going to take u plus 1 and divide it into u squared. Now, because we have to have three things here, we don't have any u's, so 0u plus 0. And now we do our long division. So I ask myself the question, what do I have to multiply this by to get a u squared? Well, that's a u. So u times this. Oh, and notice I'm putting it in a u column. So u times u and u times 1. So we get u squared plus 1 plus u. Now I subtract. This was originally positive, so it becomes negative. Excuse me, this was positive, becomes negative. If I've done things correctly, these guys should cancel. They do. And then I have 0u minus u, which is a minus u, and then I bring down the 0. And I subtract, and I'm left with a remainder of 1. So now, what I've got is that this divided into this is this with a remainder of 1 over. So this is nothing more than long division. And so now each of these can be integrated relatively easily. So we can now write, excuse me, so we could write the this guy in terms of u minus 1 and the 1 over u plus 1. So the whole point of this is that you're not using partial fraction decomposition here. You're using actually long division. And notice what we had to do is we had to take, because of the power here was bigger than here, you have to do long division. If this was the same power, you have to do this long division again. Alright, so if we do this, we now have, so I can integrate u minus 1. So the integral of u is just u squared over 2. That's where this comes from. Integral of negative 1 is just u. But we have a 3, so we have a negative 3u. This is an ln problem. So I have 3 times the ln of this guy. And we now have to go back to what? These are u's, but we originally had x's. So now you have to take your u and put it into a back substitute so that you have x's. And here's your final answer. Excuse me. And you could try to do something with these guys, but just please leave it alone. So the point here, the reason I included this problem is that it wasn't a partial fraction decomposition in the sense that from the previous problems, but it was, you have more number, this is a higher degree polynomial than this. So what I'm saying is this is something like, if you have 5 divided by 2, you would get what? 2 over 2 plus 1 over 2, and 2 over 2 is just 1, excuse me, 4 over 2, I can't do arithmetic. Right, you'd break this up into 4 over 2 plus 1 over 2, right? And if you do, I mean, if you think about it, long division, 2 into 5 is 2, 4 subtract is 1. So we're just doing the same thing with polynomials is that we did with integers. And so now you guys are experts on partial fraction decomposition.